This is a 4516 4-bit up-down binary counter. I'd like to use it to control the intensity of some high-power LEDs. Stick around. Watch us build this electronic circuit. But first, a recap. Over the past dozen or so episodes, we've gone from scratch, basically nothing, to building up a pretty good lighting circuit. Doesn't do everything we want, and let me get in to understand why that is. Right now, we've got 3 LEDs, high power LEDs, being driven by a 12-volt power supply, and we've got constant current control on it, but that constant current has actually 4 unique current paths. We've chosen 4, and each one of those 4 current paths has a parachute resistor. Now, I brought up the term parachute resistor in an earlier episode, so if you're interested, I'll link it down in the description. These parachute resistors control the level of current going through those current paths, and the current path themselves are turned on and off by these MOSFETs. Those MOSFETs, in turn, are controlled by the outputs of these 4 flip-flops, which are being clocked by basically just a clock pulse that goes up and down. So right now, these 4 current paths give us 16 different intensity levels, and that clock pulse makes it so those flip-flops are turning on and off in a particular sequence so that the light, the LED itself, starts from nothing, completely off, and works its way through those 16 intensity levels until it gets to the brightest possible level and then goes right back to 0 again. And it keeps going. So right now, we're not interested in building lights for a nightclub. I think what we want to do is build illumination for a room. And what that means is we want to have precise control over the intensity of these LEDs. Right now, we've got the intensity changing, but we don't have the control. And that's what we're going to be doing. I'm going to use this 4516 binary counter to replace these flip-flops, the 4 flip-flops that we have here right now, in order to give us that control. Now, these binary counters are pretty cool. One of the coolest things it's got going for it is that it can go up, like our flip-flops do right now, but it can also go down, which means it can count in either direction. The other neat thing about this binary counter is that it's got these really cool pins that allow you to accept an input carry and send out an output carry. Basically what that means is it lets us string a number of these things together. That turned out to be really useful in our case because these particular counters, they're 4-bit counters. And well, what we discovered in a previous video is that these 16 levels of intensity, that's what 4 bits gives us, it still gives a bit of a discrete jump every time the LED changes intensity. And so in order to smooth that out, I wanted to add another current path. If we add just one more current path to this circuit, we can then, well, with those 5 current paths, we'll have 32 levels of intensity, which should give us a nice, I guess, a more gradual change of light intensity. It's going to look good. But in order to get that, we have to add a 5th current path. And of course, these counters are only 4-bit. So in order to make that work, I had to add another counter. So I had to actually use 2 counters. So let me walk through the circuit that I've designed to accommodate these new chips. Now, most of the circuit is going to stay exactly the same. It's not going to change. What we're interested in is just replacing these flip-flops over here. So let me show you what that part looks like. Remember, all this is good. We're going to change the top right side. So we need a button that allows us to go down and a button that allows us to go up. And you could push either one of those buttons and it's going to change the intensity. How is it going to do that? Well, if we follow these circuits down, or follow these lines down, we see that we end up in an OR gate. What this OR gate is, it's saying basically if any of those switches, if either one of those is pressed, then there's going to be a signal that's going to be generated out the other side of this OR gate. And that signal goes into this AND gate over here. This AND gate is going to behave as our clock gate. So you look at another input to this AND gate and it's the clock that's coming in. So this clock is always going to be going up and down, up and down, up and down, regardless as to what we do with these buttons. But if we push one of those buttons, the OR gate is going to send a high signal to one of the inputs of this AND gate. And since the clock is coming in, it's going to serve as kind of a gate. So in other words, if we don't push any of those buttons, then that clock is not going to get through this gate. If we push one of the buttons, it's going to allow that clock pulse to get through this gate. There are two more inputs to this gate, which I'll get to in a little bit. For now, let's follow the output. As we follow the output of that clock, it goes into these 4, 5, 1, 6 chips that we have here. And there are two of them. So that clock goes to both of those chips. Now, these chips also have this carry in and carry out feature, and they're hooked up so that it just trickles down. So all the counts basically will trickle down through these. And that's why they're labeled lower significant byte and more significant byte. Maximum significant, no wait, not maximum, I don't know, MSB. And then the output of these counters are basically sending the signals off to our current path MOSFETs that we have up here. So that's where these are going over here. Okay, now we got still a few other things going on over here. You'll notice that there's a pretty gigantic NAND gate over here. What is this doing? Well, think about these counters. If we simply let them go, the counter will start at 0 perhaps, and it'll start counting up all the way till it reaches its maximum point, and then it's going to flip right back down to 0 and keep counting again. Well, we don't want that. We want it to stop. And the same thing is going to happen on the way down. If our counter's going down, then we want the counter to stop at 0. We don't want it to go past 0, because if it does, the intensity of the LED is going to go right back to the top again. How do we do that? Well, these carryouts that are coming out of these counters are pretty neat. When the up-down signal, and look, oh, I forgot to mention it. One of these buttons, the up button over here, is also connected to this direction pin. See the D over here? So this direction pin basically says that if this signal is high, these counters are counting up. If the signal is low, the counters are counting down. So what happens here is that this carryout signal is normally high. And if the direction is up, okay, follow me here. If the direction is up, that means we're counting up. And when we get to the maximum count, the carryout signal will drop down to 0. And you can see how the carryout signal is going right back into this gate over here, this clock gate. So when it drops to 0, it's going to stop that clock. And it's going to do this on both sides. It's going to do this at the maximum level of these counters. It's also going to do it at the minimum. So when this direction line is low, then the carryout signal will drop to 0 when these counters count all the way down to 0. So that's going to help us stop the count when we reach either end of these counter ranges. Now here's the other trick. Because I'm using two counters, the count range is 0 to 255. That's not what we want. We want it to go from 0 to 32. 32 because we're only using 5 of the outputs, and 5 bits gives us a maximum of 32. So we need to stop it at 32. Unfortunately, that carryout is only going to stop at 0 on the way down, which is one of the things we want, but it's going to let it go past 32 on the way up. And so that's what this commotion over here is. Basically what I've done is when all of these signals are high, that means that the Q1, Q2, Q3, Q4, Q5, and D, so that's the direction. When all of them are high, that means two things. We're counting up and the count has reached 32. Once the count reaches 32, correction, 31. We're starting from 0, so it's going to reach 31. Once it reaches 31, all of these lines are going to be high. And when they're all high, this NAND gate is going to flip that signal around and cut off the clock. Perfect. That's exactly what we want. The only other thing going on in this circuit right now is this funny business over here. Basically what we have here is we have a very small capacitor connected to the reset of both of these chips. All that this is doing is when we power this circuit up, these resets are going to be exposed to a momentarily high voltage, which is going to reset the chips. Make sure they all start at 0. But very quickly, that reset is going to go down to 0 because this capacitor is going to get charged. And then once the reset falls to 0, the chips are going to run as they should. So that's all that basically is. This circuit should give us exactly the control that we want. We got a slight problem though. All right, so you saw that I have the 4516 chips right here. I got 2 of them actually, so we are okay there. Now, how the heck am I going to implement these gates? I've got an OR gate here, an AND gate, and a NAND gate. All right, well, turns out actually I should back up a minute. In a previous video, we had the same situation where I needed an OR gate and I didn't have one. Well, we discovered that we can use diodes instead of an OR gate and they'll work just fine. We did it last time. We're going to do it again today. We're going to put 2 diodes in place and a resistor to basically function as an OR gate. We got that covered. The NAND gate, luckily, I got a chip for that. And here it is here. This is a 4012 4-input NAND gate. There's actually 2 NAND gates in there, each with 4 inputs. Well, this one's got 6. So in order to make that work, I needed to get another one. And as it happens, I have one. These are the only 2 I got, so if we screw this up, I'm out of luck. Okay, but I have 2 NAND gates. So basically what we can do here is, well, actually, let me back up a sec. I said that each one of these chips already has 2. So technically, we only need 1 if we want to implement one of these NAND gates, which is great. If you want to actually make a 6-input NAND gate and you only have 4 inputs, you can use 2 NAND gates and you OR the outputs together. And if you OR them together, it's basically the same thing as getting a NAND. So we can do that with one of these chips. I still needed the other one though, because I got another gate over here. Now notice, this is an AND gate, not a NAND gate, right? So the output of a NAND gate, remember, it's basically the same as an AND, but the output is inverted. Well, I don't actually have an AND gate. You can get one. I don't have one. But because of what we're doing here, the purpose of this gate is a clock gate. All we want to do is kind of shut off the clock when all the inputs are low and allow the clock to go through when the inputs are high. So if that's the case, we can actually use a NAND gate in this situation. All a NAND gate will do is it's going to invert that clock. But we don't care. The clock is just going up, down, up, down, up, down, up, down. If we use a NAND gate, it's going to go down, up, down, up, down, up, down, up. Doesn't matter, right? It'll work just fine. So we can use the other chip here for that NAND gate. Well, for the AND gate, but we're going to use a NAND gate to make that happen. This is the circuit that we're actually going to be building right now. So we can clearly see that that first OR gate has turned into 2 diodes. We're going to use the light up kind. So remember, we can use either a regular diode or an LED. And these 2 chips over here, these are the 4012 chips you saw earlier. So there's one NAND gate. Here's the other NAND gate. And these 2 diodes, will use regular diodes this time to control those, which I have somewhere. I'll find them when I build the thing. Okay, so I got 2 diodes to build that. And of course, we have our 4516 counters over here. I've got a 0.01 microfarad capacitor to help us reset the signal once we get this thing going. And that is basically it. So what we're seeing on the right side over here, all of this stuff over here, these are basically the circuits for the current pass and the constant current control. So everything that's going to control our high power LEDs is already here. The only change I made is I had to squish it over to fit on one side of the breadboard. Okay, so I did squish it a little bit. That's why it looks a little bit different. But everything's there from the last time. And if you're interested, I'll make sure that I can link a link in the description so you can see how we built this circuit the last time. Other than that, nothing's changed. Squished a bit. And over here on the left side is our counting circuit. So same thing, I can post a link down there so you can see the previous video as to when we built this counter. But the purpose of this counter basically is to make that up-down signal. We have an LED over here that's basically going to be going up and down with that counter so we can see it work. And over here, these 5 LEDs basically let us know which one of those MOSFETs is on or off. And of course, these are the leads that are heading to our high-powered LEDs over here. When we get the circuit running, we should be able to see those LEDs turn on and off. So I'm going to go ahead and start to create the circuit. it works now. So if I push up, Q5 does turn on, and it stops. That's exactly what I expect to happen. So when I hold the down button, I'm able to bring the counter down to 0, and it stops. If I hold the up button, the counter goes up to the right spot and stops. Let's plug the high power LEDs in now. So here it is. I'm going to plug it in. Oh, hold on. Let me bring this down first. I almost plugged it in at full intensity. All right, so now it's at minimum intensity or off, and it's now plugged in. Let's watch what happens. Brilliant. Look at that. Beautiful high power LEDs, nice and bright. And as I adjust this, we can adjust the intensity. I love it when things work. See you next time.